Swayam Prabha. Digital India. Educated India.
So far we have been discussing systems with no mechanism for energy dissipation. That means the total mechanical energy in the system always remain constant. However, unfortunately, in reality such a idealized situation is never possible, and all practical systems will be subjected to certain amount of dissipation of energy when it oscillates. Sometimes it may be very small, almost we can consider it to be of negligible level. Sometimes it will be of reasonable magnitude, so that its effect is very pronounced. But we should always remember that all practical systems are subjected to this energy dissipation, which a common term is damping, and therefore all practical systems are damped systems. What we will do now, we will analyze or investigate systems oscillation, assuming a certain amount of damping to be present. Before we do that, before we make a mathematical model which ultimately we will solve and we will investigate, we have to first see what are the various ways energy is dissipated from a system during its oscillation. The various mechanisms which are common one is the viscous drag, which results from the friction of a solid object when it moves in a fluid, and when it can be treated to be laminar motion, that means Reynolds number is low, or the system behaves in a linear fashion. We will see that very soon. So this kind of damping is called viscous damping. The next mechanism is energy loss due to solid friction between rubbing solid surfaces. This type of damping is called Coulomb damping. Say for example here, if a pendulum oscillates here. Now the pendulum, its whole body, the rod, etc., they are all having a relative motion with the surrounding air or whatever fluid it may be immersed in. That will give rise to dissipation of energy, and it will give rise to a viscous damping. Sometimes we may find, say for example, the pin of the pendulum in its hinge. If it is not properly lubricated, that may give rise to a solid friction between the housing or the journal of the bearing and the bearing itself or the pin. So similarly, there can be other situations where a vibration or vibrating system may involve two solid objects rubbing against each other, and that will give rise to Coulomb damping. Now, for example, if we take a simple cantilever beam and or simple beam rather, and go to space and hit it, and it starts vibrating, and we leave it there. So whether that vibration, neither there is any fluid surrounding it, so that there can be any viscous damping, nor it is having any contact with any other solid object, so that it can give rise to solid friction damping or Coulomb damping. But in such case, will the vibration remain constant, or whether the energy will remain constant, that is, there will be no dissipation? There also there will be dissipation, because during any deformation of a solid object, there will be internal friction. That is a very complex mechanism. We will not go into it, that how when the layers of molecules rub against each other, the grain boundaries may have relative movement against each other. All these things give rise to certain amount of conversion of mechanical energy into lower forms of energy like heat, and such damping or such energy dissipation is called internal friction. This is called hysteretic damping or material damping. And other possibility of dissipating energy is in the form of radiation, that can also give rise to energy dissipation. However, we should keep in mind that the first three are of much bigger importance so far as engineering systems are involved. There are also most commonly involved problems we will consider will involve viscous damping, the reason I will discuss. Then we will also discuss Coulomb damping or the dissipation due to solid friction, and we will also discuss quickly about internal friction or hysteretic damping in materials. First, let us take viscous damping. Let us consider this is the sectional view of a cylinder with a piston inside. A piston is connected to one rod and cylinder is connected to another. The inside of this is filled up with some kind of a viscous fluid, some oil or something like that. Now the cross sectional area is say A. A1 is the cross sectional so this piston it has fine holes drilled into that, through holes, and the total cross sectional area of all these holes which have been drilled is say A1. Now if I keep this end fixed and try to pull this end with a speed say x dot, that end is fixed. Now we know that to do that, to draw it in this direction with a speed x dot, we have to apply a force Fd. Now how Fd depends on x dot, that is our problem. So what happens when we pull this piston in this direction, fluid in this side goes through these holes to the other side, because fluid is incompressible. When we try to reduce this volume, obviously the fluid has to go to the other side where a similar amount of volume is created. So the velocity of the fluid passing through the holes which have been drilled in this piston will be how much? Now we know that what is the amount of fluid which has to go per unit time. It will be the speed with which it is coming to this side into cross sectional area. We ignore the cross sectional area of this rod, etc., which we can ignore. So therefore the rate at which total volume of fluid must flow to this side is how much? It is cross sectional area A, and the rate at which this volume is reducing, that is x dot into A. And the cross sectional area through which it flows is A1, total amount. So the velocity through this hole must be this. Now we also know that the fluid resistance or resistance to fluid flow it will be something which will depend on the cross sectional area of each hole, length of the hole, all those things, surface finish, all those things. But overall we designate it by quantity R. And we know that any passage if fluid flows at a rate V and the fluid resistance of this path be R, then the difference in pressure from this side to this side, say P1, this side say P high, P low, higher pressure side, lower pressure side, that is the difference of pressure on the two sides will be given by a quantity or proportional to this, whatever you may say. So therefore, what we find now, the piston, the two sides will have different pressure. What will be the pressure on this side? Will be P. Higher pressure will be on this side, and lower pressure will be on this side, because fluid is flowing from this side to that side. So this side is higher pressure. How much is that? P higher into cross-sectional area A. Again, we have made it approximate, ignoring the cross-sectional volume of that. On the other hand, pressure from this side which will be lower pressure, the total force will be, and the force which we are applying here, Fd, the whole thing has to be in equilibrium because there is no acceleration. And so this force balance tells us Fd is equal to and this is equal to the resistance of the total resistance of the path of all the holes together into the speed of the fluid passing through that, which is x dot A by A1 into A. So therefore, we find that this is nothing but R A square by A1 into X. So effectively what we find that Fd is proportional to X dot. All these things of course are valid, as you know, only for laminar flows. So therefore, we are considering that for a suitably viscous fluid the flow will be laminar. Or we can write the constant of proportionality, which is represented by this, by a coefficient which we call C. The coefficient is a special property or coefficient for a particular damper. Its dimension, kind of fluid, everything, it will depend on that. So therefore, we find that we get the damping force linearly dependent on the velocity of the object. So therefore, viscous damping in its normal form provides a force which is a linear function of the velocity. That is why it is so easily amenable to solution, because the differential equation which we will get will be a linear differential equation that we can solve. So with this little introduction to viscous damping mechanism and the job of a damper, we will now take up our single degree freedom system and its lump parameter model. So the dampers are generally, viscous dampers are represented by this diagram. So when this is moved with a velocity x dot, it needs a force Fd which is equal to, with of course this side fixed. So now therefore this damper here, its predominant property is providing a damping force. We will ignore its mass, we will ignore the elasticity of the whole system, that means any kind of stiffness which may be present, which will be present. So therefore, this becomes again an ideal situation without any mass, without any stiffness, that means it is perfectly rigid. Its only job is to provide a damping force. So the lumping of this damping parameter will be to this idealized situation. So let us now draw, or let us now take up the simple case of a single degree freedom system with viscous damping and its free vibration. So we take up now the case of free vibration of a viscously damped single degree freedom system. So we just go one step ahead of the first and the simplest model where there was no energy dissipation. The lumped parameter model So this is the lump parameter model of this system, and of course in its equilibrium position will be such when it has been left to itself, that means this spring has taken its equilibrium, the natural length position. Because if the spring is pressed or compressed, it will again slowly either go out or come back, so that this mass can come to that position when no force is acting on it. That means when both it is stationary, so no viscous damping force, and the spring is at natural length, so no compression or tension force in that. Now when we displace it, mass is here, the forces which will be acting, there will be two forces now, as we know that at any instant its position is x, so therefore there will be a spring force which will be k into x, and if at this instant its speed is and it is moving at a speed x dot, then here this damper will provide a damping force also like this. This will be pulled, it will try to prevent its expansion, this will be the force, and its acceleration, algebraically positive acceleration in this direction. So therefore the Newton's second law for this will be what? It will be m x2 dot must be equal to the total force in this direction, which now is minus kx minus ex dot, or so this becomes the equation of motion of the mass when viscous damping is present. That means this term has come. Now to solve this differential equation, we proceed in the standard way. That means let the solution so when you substitute it here, we get m s square e to the power st plus cs e to the power st plus k e to the power st equal to 0, and the characteristic equation what we get for s is a quadratic equation like this. Quadratic equation will yield two values of this s, s1 and 2, which you can write simple, minus c plus minus c square minus 4 km sometime you can write it like this. Now, and the general solution, general form of solution for the motion, that is xt, we can write as a say e to the power minus c by 2m plus c by 2m 1 minus 4 km plus b so a e to the power s1t plus b into e to the power s2t. This is the general form of solution. Now, what will be the nature of solution? Let us first see before we proceed further. Now, you can see that a situation that when 4 km by c square, this quantity is less than 1, so case 1 where 4 km by c square is less than 1, that is c square is more than 4 km. Under this situation, this whole quantity is a real quantity because this is real, these are all real, and as you can see that since it is 1 minus something, so this quantity will be less than c by 2m because this is less than 1, and since this is negative and this is positive, this whole quantity will be a negative real quantity. So e to the power a negative real quantity into t is nothing but an exponentially decaying term with time. So x, the first term, will decay as t progresses. Go to the second term. Here again you find that this is a positive quantity less than 1, and this is negative, this is negative. So this one again is a negative real quantity, and therefore this is also nothing but an exponentially decaying term, but here the decay will be faster. So both the terms are exponentially decaying with time, and so we will have and this kind of motion, that means it is going to just asymptotically going to 0, is called aperiodic motion. It is not going to be a periodic motion where the equilibrium position is crossed again and again repeatedly. There is no question of any period. And this situation which results in this kind of a motion, this condition is called overdamped. So, when the damping is very strong and it is so large that it is more than this quantity, then the system does not execute any oscillatory motion. It decays as the time increases, resulting in an aperiodic motion. The next possibility is case 2, when C square is equal to 4 km. This is a critical condition, and with this condition, what we may say, which satisfies this condition, C is called CC, that is and the system is critically damped system. So, in this case, when C square is equal to 4 km, that is when C is a particular value, which you also indicate by the letter C subscript C, we call it critical damping coefficient, and with this situation the system is called critically damped system. Now, what will be the nature of solution in this case? We know that S1 will be equal to S2 will be equal to minus C by 2m. So, when the two roots are equal, the general solution is x t is equal to a plus bt into e to the power st, which is minus c by 2. Here again we see that as t increases, this increases perhaps linearly. Of course, we have to find out what will be the nature of A and B. We will discuss that later. But this is an exponentially decaying term, and so as a result, here also we get aperiodic motion. So, here for example, in an overdamped case, we displace the mass and leave it, so it will go and approach the equilibrium position asymptotically. Here also, if you just pull it and leave it, it will again go aperiodically and asymptotically approach the equilibrium position. The only difference with the overdamped case in this will be here it will approach the equilibrium position at the shortest possible time. So, in situations where we want a system not to execute oscillatory motion, there are many such situations. We will take up some examples, like say door closure. When you open a door and if you leave it, if it has to execute an oscillatory motion, it will go through the door frame with the maximum velocity, which you do not want, because then it will bang somebody and it is not a very desirable situation. On the other hand, what we would like it to go and close at its equilibrium position with 0 velocity or negligible velocity. So therefore, we will try to put damping which will provide aperiodic motion. At the same time, we don't want this closing to take place enormous amount of time. We want this to close as quickly as possible. Say the room is air conditioned. So therefore, we don't want the door to take a long time to close when left. If somebody comes in and he leaves the door, it should go and close at the shortest possible time. So therefore, in such situations, we provide the system with critical damping. Another example is, say, cannon recoil system. When cannons are fired, they get a recoil, and then if it is only a spring, then it will keep on oscillating, which we don't want. So we want the cannon to recoil, and then while it goes on this side, the damper is attached. And so it should go asymptotically at the quickest possible time, and again we provide critical damping. Same is the case with shock absorbers in many vehicles or suspension systems, where we want the system to approach the equilibrium position without oscillation at the quickest possible time, and that's where the importance of critical damping lies. In practice, we keep it slightly above critical damping, because due to temperature rise or something, if the viscosity of the oil which has been put inside the dashpot reduces, then it may go below the critical damping and its system may have oscillation. So therefore, generally it is kept very near critical damping, slightly above. Now, it is now important to see that what happened in the other case, that is the only case left. When damping is small and it is less than 2 square root of km, then the system is called underdamped system. And what will happen to these roots? We will have roots will be now if C square is less than 4 km, then obviously this quantity is positive or more than 1. So whatever you put inside the square root is a positive quantity, and that is okay. But we have multiplied the whole thing by -1, and so this I has come. So therefore now we find that the two roots are complex. There is a real part and there is a complex part. And the solution So this will be the general solution. We can rewrite it slightly in a different form. before we proceed further, it will be desirable to have certain symbols or certain concepts developed here. So, it is not generally very convenient all the time saying C square is more than or less than or equal to 4 km, because this particular critical damping coefficient what we are telling, it is only for the particular configuration here. A different configuration can give a different relation, as you will see while solving some problem. So, there should be a better way of telling that whether a system is damped or under damped or over damped or critically damped. What we do, at least for this particular case, if we see, say if we find that Cc is equal to 2 square root of Km, and this quantity C by Cc, the ratio of the actual damping coefficient and the critical value which just distinguishes between the aperiodic and periodic motion, as you will see, is defined as damping factor. And when zeta is more than 1, it is over damped. When zeta is equal to 1, critically damped. And when for a system zeta is less than 1, it is under damped. So, I think we will do that, but before we proceed further, just to comment on this nature of solution what we have got. As you can see, this is an exponentially decaying term, but inside this we have a quantity into e to the power I theta plus b into e to the power minus I theta. We all know that this represents a harmonic function of time. We will write it down later after we use this concept and do the necessary changes here. So, therefore, here we will find quantity C by 2m can be written as C by Cc into Cc by 2m, and here this is zeta obviously, and Cc is 2 square root of Km for this particular system we are doing divided by 2a, and this is equal to 2 zeta, and this becomes square root of K by m, and this is equal to, we know it is the undamped natural frequency of the system. That means the system we are investigating, if you take out the damper, whatever will be the natural frequency will be square root of K by m. So, wherever we have C by 2m, we can replace it by this quantity. So, therefore, for the 3 cases, let us write the solution using this concept. So, for case 1, the solution will be, or the general solution will be now, it is better that we do the general solution. It will be A e to the power minus C by 2m is 2 zeta omega n, we have already seen. C by 2m is 2 zeta omega n, plus again C by 2m is 2 zeta omega n square root of 1 minus. Now, this is critical damping coefficient square, Cc square. So, it will be 1 by zeta square. plus b e to the power minus 2 zeta omega n minus 2 zeta omega n square root of 1 minus 1 by zeta square So, this is the general solution. We can write it in this form then, e to the power minus 2 zeta omega n t is common in both the cases. So, it goes inside, a outside, e to the power. Now, if I write it zeta 1 minus zeta square or zeta square minus 1 here, so we get 2 omega n zeta square minus 1 t plus b e to the power 2 omega n zeta square minus 1. Now, depending on the value of zeta, whether it is more than 1, equal to 1 or less than 1, our solution will depend. Of course, when it is equal to 1, then you have to follow this form of general solution, that you have to keep in mind, not this form. So, now when we have the case 3, that is zeta is less than 1. So, xt can be written as e to the power minus 2 zeta omega n t and a e to the power. Now, zeta is less than 1, so this quantity is negative. So, we can write this in this form 2 I omega n 1 minus zeta square t plus b e minus 2 I and this is nothing but of this form. If we express e to the power I theta and e to the power minus I theta, you will ultimately get it will be something like a1 sine I think these two cancel. Sine omega n 1 minus zeta square into t plus b1 cosine omega n Now, observing this, what we have got now in the underdamped case, in underdamped case, we find that the system is oscillating with time. But if it had been only this, it would have oscillated like the case when we solved first without any damping. But the whole thing is multiplied by an exponentially decaying function with time. So, the resulting motion is going to be the resulting motion we find is slowly decaying. whereas in the previous cases we know that they are aperiodic motion. Same thing in the overdamped case. Now we have oscillation, but the magnitude of oscillation is gradually decreasing. So therefore, what we have learned till now is that for viscously damped simple spring mass dashpot system, depending on the magnitude of the damping coefficient of the dashpot, there can be three possible situations. One is called overdamped, when the damping factor is more than 1, then the resulting motion of any disturbance is an aperiodic motion, whereby the system approaches its equilibrium position asymptotically. With the critical damping coefficient, when zeta is 1, it is the similar kind of behavior, only thing it happens with the quickest possible time. On the other hand, when the damping factor is less than 1, system is underdamped and it executes a oscillation when disturbed, but with a diminishing magnitude as time progresses. We also notice another important thing beside the fact that the vibration diminishes in its magnitude with the progress of time. The frequency of oscillation, which we call damped natural frequency, is also slightly lower than the natural frequency of the system if we take out the damper. Without damping, it will oscillate little faster with a higher frequency, whereas if damping is present, then it will be a little less than the natural frequency without damping for the same system. So this is called damped natural frequency, which is nothing but omega n into 1 minus zeta square root. Now I think if we want to investigate further cases, we will look into the general solution. Before we attempt the general solution, a further discussion of the impact on the resulting motion of the nature of the initial conditions on which A and B will depend. Before that, let us quickly look into the matter of underdamped vibration as you have seen here. Now, if a system vibrates, is given by x or say we can write it in another form. That equation can be written in this form. These two constants A1 and B1 can be replaced by two constants as x and phi. We have seen it when we discussed the harmonic oscillation in the earlier lecture. So, the amplitude, for example, suppose this is the nth amplitude, and say the next one is n plus 1. Two successive peaks we are taking. What is the time taken for the system to go from one peak to another? Obviously, it is nothing but the time period. How much is this time period? Time period we know that 2 pi by the damped circular frequency, or undamped natural frequency into 1 minus. So, your x n by x n plus 1, how much is x n? X n is this for a particular time. So, therefore, it will be e to the power minus zeta omega n t into x. And what will be the time for the next peak? It will be t plus tau. And this is nothing but e to the power zeta omega n. How much is zeta omega n tau? Omega n tau, you can see from here that omega n tau is equal to 2 pi 1 minus eta square here. So therefore, if I take natural log of this quantity, we get 2 pi zeta Now this is a measure of the intensity of the damping. That means how fast the amplitude is reducing. Higher this value of this ratio of the two successive amplitudes, larger is the damping. And when you take the natural logarithm of the ratio of the two successive, you can see it does not depend on n. It depends on any two successive amplitude will provide this quantity, and this is called logarithmic damping. And this is a measure of the intensity of the damping. As you have seen, it is, of course, it has to depend on zeta, as zeta represents the damping. So, and when zeta is small, which happens many of the situations, then this quantity logarithmic damping delta, that is the standard symbol, is equal to 2 pi zeta. Another way, another method of representing the intensity of damping is by how much energy is being dissipated per cycle and its ratio with the maximum energy during that cycle. Now when the system is vibrating, any cycle you take, say either this or any such thing, the energy is obviously maximum at the beginning of the cycle because energy is continuously being dissipated. So if we take the loss of energy divided by the maximum energy, suppose at the beginning of the cycle energy is E1 and at the end of the cycle the energy is E2. So then this is E1 by E2 by E1. This is this quantity, which is again nothing but 1 minus E2 by E1. Now we know that what is the at this the peak position, whole energy is in potential form, and obviously it is nothing but the strain energy in the spring, that is half K and x, say n plus 1 square, if that is the energy at the end of the cycle, that means at the next peak, divided by energy at the beginning of the cycle, that is the previous peak. So this what we get here is nothing but delta E by E1 is equal to 1 minus x n plus 1 square by x n. And this is equal to 1 minus, how much is x n plus 1 by x n? E to the power minus zeta omega n t, or since omega n tau is equal to 2 pi zeta so it will be just opposite, yeah. So this will be 1 minus e to the power, and this quantity is delta. So this will be minus 2 delta. If we expand it, 1 minus what will be this? Infinite series. So approximately 2 delta. So again we find that this quantity, the amount of dissipation of the energy for a circle during a cycle divided by the maximum energy during the cycle is nothing but double the logarithmic decrement. So this is another way we can represent energy dissipation through the amount of energy dissipated per cycle, and you can see the relationship is again there with the logarithmic decrement. So the measure of the intensity of damping, which we do with the help of damping factor, but during experiment when we do, we try to figure out that how quickly the amplitude is decreasing, and we take two successive amplitudes and find out the logarithmic decrement. Sometimes it may happen that two successive amplitudes are very close to each other, and therefore there may be a large amount of error involved. So what we can do, we can take a p number of cycles in between, and so what we can do, we can take the ratio of logarithm. What we can do is take the logarithm of x n by x n plus p, not just the next one, but after p cycle. And obviously you will find this will be what? Here you see this will be p tau. That means omega n tau is 2 pi by 1 minus zeta square. So it will be 2 pi p, and obviously this is going to be or simply p delta. So delta can be found out in such cases. And finding this ratio between two amplitudes widely separated can be much better in its accuracy, and that is another technique by which logarithmic decrement is found out. Now if you want to find out the damping factor, you can find out damping factor from delta by using this equation. The delta is given by this, solve this to get zeta, and if zeta is really very small, then we can even use this directly, that you divide delta by 2 pi, you get zeta, and so on. Then you can also find out the amount of energy dissipated per cycle, and all types of investigation is possible. So next what we will do in the next lecture is that we will investigate in great detail that what kind of initial conditions can lead to what kind of motions based on the amount of damping present in the system.